Hello guys, so in the last class we had spoken about how the optical isomerism is detected in the molecules, and we have spoken about two basic terms. One is plane polarized light, how do we generate plane polarized light, and what is the effect of organic molecule on that plane polarized light if that molecule is optical. So basically in terms of plane polarized, how to find out whether a compound is optical or not optical, that we had understood. And we had spoken about the chiral centers. Chiral centers, not only chiral carbon, chiral centers which can be carbon or a non-carbon atom also. Now in today's class we'll be talking about chirality, and we'll be talking about the symmetric elements which can be present in a compound. Okay, so first let's start with the chirality. So now when I'm using the term chirality, chirality is a different term than the chiral center. Chiral center's condition, I told you that the element must be sp3 hybridized, and in all the four bonds there should be different molecules present. Then your atom will be called as chiral atom, or that particular atom will be called as chiral center. As well as I also told you in the last class that presence of chiral center is not a mandatory condition for a compound to be optically active. That means if the chiral center is present or not present, that cannot define whether your compound is optically active or not. But if in a molecule there is one single chiral carbon, not chiral center, chiral carbon, then that compound must be optically active. So all these things we had discussed in the last class. We had seen the exception how nitrogen, even though it is sp3 and the four different groups are attached in tertiary amine, still it does not contribute in the optical activity, and hence the compound becomes still optically inactive. The reason for it, I told you, I'll be telling you in the next few classes. Today we'll be understanding chirality, and that is a different concept than chiral center. So you cannot mix up chirality and chiral center. Chirality is something else and chiral center is something else. They don't have relation between them. So what exactly is chirality? Chirality is the property of a molecule or property of any substance. Chirality is a property of a molecule or any substance which, if we try to divide it into two equal halves, it cannot be divided into two equal halves. So for example, let's say if you talk about a rectangle, okay, and you cut it, you can divide it into two equal halves. You talk about a chalk can be cut into two equal halves. You talk about anything around you, you see there are certain things which can be divided into two equal halves, and there are certain things which cannot be divided into two equal halves. So the property of a molecule or property of a substance because of which it cannot be divided into two equal halves is called as chirality. Okay, so the compounds which cannot be divided into two equal halves are called as chiral compounds, whereas the ones which can be divided into equal halves are called as a chiral molecule. So again, I'm repeating, when a substance cannot be divided into two equal halves, now that substance, I'm talking about any substance in general, or if we take a reference of a molecule and if we try to cut it through a certain plane and we cannot cut it into two equal halves, that means that particular molecule is chiral molecule. So here let's look at the definition. Chirality is the property of a molecule, which means the molecular structure or compound's 3D structure cannot be divided into two equal halves. Okay, now we have to understand how it is related to your optical activity. What is chirality? What is exactly we mean by two equal halves, and why do we need it that way? Okay, chirality is a property of a molecule because of which a molecule cannot be divided into equal halves. So we have seen different combination. As I mentioned that your chiral centers and chirality has no relation. It doesn't mean that if you have a chiral center, the molecule will have chirality, or if you don't have chiral center, you won't have chirality in the molecule. That is not there. We have all type of combinations. So we have different cases where in the molecules you have a chiral center present in it, but chirality is absent. That means the molecule still can be divided into two equal halves. Okay, even though there is one chiral center. We have such cases also where we have no chiral center present. That means the molecule has no chiral center at all, and still your molecule cannot be divided into two equal halves. And third such case also we have seen, where chiral center is also present and chirality is also present. So presence and absence of chiral center is not affecting chirality. Chirality is a different phenomena altogether, and chiral center is a different phenomena. Chirality is important for a compound to be optically active. If chirality is there, your compound will be optically active, but that's not the case for chiral centers. If chiral center is present there or not present there is not going to affect the optical activity of the molecule. So any compound which is optically active has to be chiral, but the presence of chiral center is not mandatory. So these things may sound a little confusing right now, but when you'll solve questions, when you'll solve some examples, you'll get to know what exactly this means and how can we implement this. Now, when I told you that the chirality is nothing else, but when a molecule's 3D structure cannot be divided into two equal halves, that is called as chirality. How would we decide whether a compound is chiral or not? How will we check? We are not going to see the 3D molecule all the time, and we are not going to cut it all the time and then analyze. So what is the way how to analyze whether a molecule is chiral or not? The way of analyzing the molecule's chirality is you take a molecule and take its mirror image and see whether these mirror images are superimposable or not. Now, here, what is the meaning of superimposability? Let's understand. So first of all, you will have to understand the superimposability, then only you can understand the chirality. So now, let's say if you talk about my hand, okay, this is the hand. So now if you talk about this hand is the mirror image of it. Both are mirror images of each other. Now, if I want to superimpose my right hand on my left hand, can I do it? Is it superimposable? Let's see. So this is my hand and this is my other hand. So if I try to put it there, it looks like that it is superimposable. Why? Because they are both touching to each other very properly, but superimposability doesn't mean the touching of the surfaces. Superimposability means that it should get indulged completely and both should look like as if it is just one thing present. That means if you see the surface of this hand and surface of this hand is merging, but what about the nails? The outer surface. Outer surface is not merging with the outer surface of the other hand. The nails are not touching each other and not merging with each other. The outer skin of this hand and outer skin of this hand is not merging with each other. Hence, these two hands are looking like two hands only, and they're not looking like as if they have clubbed and have become one. To get a better understanding, assume if the hand wouldn't be that straight or it would be little curled up like this. Now you try the superimposability. This is the mirror, this hand is the mirror image of this hand. Now try to impose. Now what is happening? Now see. Only the points up here on the fingers are touching each other, and it's not able to indulge completely and is not capable of making itself one. Similarly, if you see yourself in the mirror, let's say you are standing in front of mirror is the mirror, I mean whatever is coming in the mirror is your mirror image. Now you try to go and superimpose yourself on that mirror image. Can you do that superimposability? No, because your nose will touch to the nose. It won't get indulged. Now, if somebody says that you can turn it around, turn your hand and then do it, is it possible? No. When I say superimposability, it should completely get indulged, and then every single surface should join with each other and it should become one. Okay, the same way how, as I mentioned, that your mirror image in the mirror, you, no matter whatever you do, you go straight, only nose will touch to nose because it's a 3D structure. You can see very clearly. Many things will not touch each other. Many things will not get indulge each other. If you rotate to 180 degree and then you try to go like this, then it will not superimpose. So there is no way you can superimpose with your mirror image. So you yourself is chiral, your hand is chiral, your hand possesses chirality. This is chirality. When you cannot combine, when you cannot completely indulge, completely superimpose the things, only the surfaces are superimposing, not each and every part of the of any substances completely imposing, completely indulging and becoming one, then it is not called as chirality. Then it is not called as superimposable. Now let's take one example using a molecule. Assume I have this molecule. Okay, Now in this molecule, what I have is this is one group, this is the another group, this is the third group, and this is the fourth group, and there is a carbon in the center. Okay. Now I have taken the exactly same molecule, exactly same molecule. Okay. Exactly same molecule. This is same molecule. Now if I try to superimpose, basically the same substances will superimpose. Here it is a 3D, I cannot. So it's like your yellow is touching yellow. Okay, look at it. Yellow is touching yellow, black is touching black, white is touching white, and your blue ball is touching blue, and the purple ball is touching purple. This is superimposable, completely superimposable. Each and every part of one molecule and the another molecule is getting superimposed because these are identical. These are identical. Okay, these are identical, and when you're trying to superimpose, it is getting superimposed. I hope you are able to see it. Okay, now let me show you how what is non-superimposability in the same molecule. Just give me a moment. Now look at this molecule, okay, and look at the another one. These two molecules are mirror images of each other. Yellow is in front of yellow, purple is in front of purple, this blue is in front of blue, and the white one is at the back, and this white one is at the back. So look at it. So this one and this one, these two are mirror images of each other. This two and this two, or let me just hold it in such a way that it becomes more clear. This and this are mirror images of each other. Right? Now you try to superimpose this mirror image on this molecule. Just try. Just think. Think on your own, and then I'll show you practically. Superimposition I can do by directly putting up here. Okay. Is it superimposing? Is it superimposing? No. On purple, the white ball is coming. On this purple, the white ball is coming. On the blue, blue is coming. And on the yellow, yellow is coming. So these two parts are not superimposing. Okay. Now, if somebody says that you can rotate it, you can do some rotation and then try doing it. Let's rotate it. Okay. Now I do it. Is it superimposing? No. Now on blue, the purple thing is coming, and on the other blue, the purple thing is coming. Okay. On the white, white is coming. On yellow, the yellow is coming. Let's rotate it in certain other way. Let's try it a few more times. If I rotate it further, am I able to superimpose? No. So you rotate it in any direction and you try to superimpose. It is not superimposing, no matter whatever you do. Just concentrate, just see what I'm showing you. In either way you rotate it and the molecule will not superimpose. Its mirror image is not superimposing on it. This compound's mirror image is not superimposing. This is the mirror image of this compound. These are not superimposable. So this is non-superimposable phenomena. No matter in whichever angle you rotate it, no matter whichever angle you rotate it, it will not superimpose. Okay, whereas what was the superimposability? I had shown you when everything was just touching the other substance. Your yellow ball was touching yellow, black was touching black, purple was touching purple, and blue was touching blue, white was touching white. That was superimposability. So basically there are two kinds of molecules. One type of molecules have their mirror images which can get superimposed, whereas there are some molecules their mirror images do not superimpose on them no matter whatever you do. And such compounds which have such mirror images which do not superimpose on them are called as chiral molecules, and that phenomena is called as chirality. So let's see in short what we are trying to say. If a molecule is non-superimposable on its mirror image, then the molecule is called as chiral, and both the mirror images, because this is not superimposable on this and this is also not superimposable on this, then this is also chiral and this is also chiral. Both are individually chiral. If a molecule has non-superimposable mirror images, then both of the images are chiral or possess chirality, and the molecule itself is chiral. A very important thing what we have discussed earlier, that chirality doesn't mean the presence of chiral center. chirality gives optical activity to a molecule, not the chiral centers. So it is not necessary that all chiral compounds what we have will have chiral carbons or chiral centers present in them. Okay, presence and absence of chiral center is not affecting the chirality. That is the main key, and any molecule which is chiral is going to be optically active also. How will we judge whether a molecule is chiral or not? We will judge it by its mirror image. If its mirror image is superimposable, then it's not chiral. If its mirror image is non-superimposable, that means it's chiral, and if it is chiral, that means it is optically active. Okay, now every single time you cannot draw the mirror images. You have certain different type of, most of the molecules which we see are in 2D plane. How will we decide the chirality? Just by looking into the mirror. I mean, we can't always, I mean, this is the simple molecule where carbon has 4 different groups attached to it. But when you talk about the big complex molecules, it's not easy to always keep thinking or imagining what would be the 3D structure and then figure out its mirror image and then see whether that is superimposable or not. So to understand that fact, that what is superimposability and the mirror image is superimposable or not, we understand the symmetry in a molecule. So there are some symmetry elements which we talk about. Especially we talk about two symmetry elements. One is plane of symmetry and another is center of symmetry, which helps us in understanding whether the image of a molecule will be superimposable or not, or whether the compound will be chiral or not. So that we'll be learning now, the symmetry elements, how those symmetry elements play their role, what exactly those symmetry elements mean, and how to check in a molecule. So last thing about the chirality is, as I mentioned, chirality is necessary and sufficient condition for a molecule to be optically active. That means you don't have to look for the chiral center. Again and again I am repeating this thing. Chiral center's presence doesn't mean that your molecule is going to be optically active, but the presence of chirality, or if the molecule is chiral, that definitely ensures that your compound is optically active. So chirality is the necessary and sufficient condition for a molecule to be optically active. The presence of chiral carbon in any compound does not guarantee the chirality in a compound, and hence does not guarantee the optical activity in the compound. Okay, so this is about chirality. Let's move to the symmetry. If you have not understood anything in this, ask me in the doubts class. So now we have understood what is chirality. Just to recap very quickly, you may find me quite repetitive, but it is very important for you to remember all this about chiral centers and chirality. So what exactly is chirality? When a molecule's 3D structure cannot be divided into two equal halves, then it is called as chirality. Or in the other words, you can say when the mirror image of one molecule is not superimposable on the other. Then, I mean, when you have taken a molecule and its mirror image is not superimposable on it, then it is called as chirality. Now, there is no connection between chirality and chiral center. The presence and absence of chiral center does not affect the optical activity or does not ensure any kind of optical activity. Whereas, if the chirality is present in the molecule, then the molecule will surely be optically active. It is sufficient and necessary condition for a molecule to be optically active. So now we have got a very detailed idea about chirality. Next, we have to understand how to figure out this chirality in a molecule. We cannot all the time think about the 3D structures. We cannot make all the 3D structures and then keep them together and then try to superimpose. That is practically impossible. So we have to figure out what are the other ways to check the chirality in the molecule. And it has been seen the molecules, or this has been derived from all the information what we have gathered about the chirality, that any molecule, if it is not symmetric, then it will have the chirality within it. So what is symmetry? There are 23 symmetry elements or symmetric elements in a substance. There can be 23 symmetric elements can be there, which probably Nimir sir will explain you in his physics class. But when a molecule does not possess symmetry, then the molecule is chiral. Okay, so when I am saying it is not possessing symmetry, what does it mean? If you talk about, I'm not going to teach you about all the 23 elements of symmetry, but we'll definitely talk about few important symmetric elements which we have to look for whether these are present and absent, and then we will decide whether a particular compound is symmetric or not symmetric, and then we will decide whether a compound possesses chirality or does not possess chirality. So there is first term what I'm going to discuss is, which I have not mentioned in the slide, and that is asymmetric molecule. This is asymmetric molecule. What exactly is asymmetric molecule? As I mentioned, there are 23 symmetry elements, and absence of symmetry is the mandatory condition, or you can say if the molecule is not symmetric, then it possesses chirality and then it shows optical activity. So not being symmetric is very much required for a compound to be optically active. If all the 23 symmetry elements are absent from a molecule, that means that it possesses no symmetry at all, then the molecule is called as asymmetric. For example, if you take this molecule, okay, so this is the carbon and then 4 different groups attached to it. So basically this is the chiral carbon and this is the chiral center, but we are not talking about the chiral center right now. So this this particular carbon does not possess any kind of symmetry. I mean, no way you can cut it into equal halves. It doesn't have any kind of symmetry, not from the center, not from the plane, and there are other 23 molecules. No way you can just break it into two equal halves or cut it into two equal halves, which becomes superimposable. So there is no symmetry at all in this molecule. Okay. And we can also see one important thing, that it has a carbon which has all the 4 different groups present on it. So basically this is the chiral center. This is the chiral carbon. So now if you remember what I had told you about, if there is one chiral center in the molecule, just one, not chiral center, sorry. If we have one chiral carbon in the center, then the molecule possesses optical activity. It will show optical activity. This is the reason why it will show optical activity, because it will have no symmetry element at all. And when it has no symmetry element, it is very much sufficient and ideal condition for a compound to be optically active. As I told you, the symmetry, when the symmetry is not there, the compound will be optically active. Here no symmetry element is present, so this is the perfect condition for a compound to be optically active. So asymmetric molecules are those molecules in which all 23 symmetry elements are absent. An example for this is any compound having one single carbon as a chiral center. When there is only one single chiral carbon in a molecule, that actually denotes the asymmetric molecule, because it will have no symmetry at all. None of the 23 symmetry elements will be present, and hence it will definitely show you the optical activity, because that is the perfect condition for optical activity to be seen. Okay, now we have to see that we cannot analyze all the 23 symmetry elements, but we can analyze some symmetry elements, which, I mean, there are cases where some other symmetry elements are present, few of the symmetry elements are present, and still the compound is optically active. But out of 23, 2 symmetry elements are mandatory to be absent to be optically active. Now, as I said, in this compound, all the 23 are absent, but there would be cases where there may be some other kind of symmetry present, or some elements of symmetry are present. But in that case, how will we ensure whether the molecule is chiral or not chiral? That by looking at only 2 symmetry molecules. So in general, if I have to check the symmetry in the molecule, I will not be checking for all the 23 symmetry elements. I'll be checking for only 2. And then that will help me in deciding whether the compound is chiral or not chiral. If in a molecule there are 2 symmetry elements, one is named as plane of symmetry and other is named as center of symmetry. These 2 symmetry elements, if these 2 symmetry elements are absent in the molecule, then it ensures that your molecule will be chiral. Forget about the other symmetry elements. We are not going to check them. Only these 2, if are absent, make sure that the compound is chiral. So there might be some other symmetry elements present, but we are not going to deal with. As I mentioned, lesser the symmetry in your molecule, more are the chances of chirality. Mandatory condition is these 2, plane of symmetry and center of symmetry, should be absent for a compound to be chiral. If all the 23 elements are absent, then it is the ideal condition. But if, let's say, all other symmetry elements are present, but plane of symmetry and center of symmetry is absent, then also the molecule will be chiral or must be chiral. And such molecules which possess maybe other symmetry elements. So the molecule in which 2 symmetry elements are mandatorily absent irrespective of other symmetry elements are present, are called dissymmetric molecules. And dissymmetric molecules must be optically active. If the absence of POS and COS is there, that ensures that your compound is optically active. So what we are going to do it, how we are going to check the chirality, we will be just checking the POS or plane of symmetry and center of symmetry in a molecule, and that will help us in deciding whether a compound is chiral or not chiral. We are not going to see all the 23 symmetry elements because asymmetric molecule will always be optically active, but the minimum condition which is required for a compound to be optically active is dissymmetric molecule. That means at least it should not have POS and COS. Okay, so asymmetric molecule is an ideal molecule for being chiral or to possess chirality, but dissymmetric molecules also possess chirality because they don't possess two symmetry elements. One is POS, one is COS, which is extremely mandatory condition. So these two symmetry elements should be absent for a compound to be chiral. Now let's understand what is plane of symmetry. Let's get into detail of what is plane of symmetry. So what is plane of symmetry? Plane of symmetry means when you take a substance and cut it through a certain plane and then you get two equal halves. Those two equal halves must be mirror images of each other. If you are able to cut a particular substance in two equal halves and those two equal halves are mirror images of each other, then it is called as plane of symmetry. For example, if I've taken this pen, look at this pen. If I cut it like this, like horizontally, will I be able to divide it into two equal halves? Yes, I will be able to. I will be able to cut it into two equal halves, right? Exactly same way, if you, let's say, take this book, right? Can you cut it into two equal halves? Yes, I can do the slice cut. I can do the slice cut like this, and it will be divided into two equal halves, right? Can I cut it through this plane and it will divide into two equal halves? Yes, it will, right? So basically, when you cut it through a certain plane and it is able to divide into two equal halves and those two equal halves are mirror images of each other, then that plane is called as plane of symmetry and the molecule possess POS. Okay, for example, now let's take this hand. If I try to cut it into two equal halves through a certain plane, what can I do? I can cut it from here, from the center. Is it giving me two equal halves? No. I mean, two equal halves means, are those two halves are mirror images of each other? No. If I cut the slice cut, if I do the slice cut of this hand, then what will happen? One half will be this surface part, okay, and the other half will be the one with the nails. So are those halves are mirror images of each other? No. If I try to cut it diagonally, will I be able to cut it into equal halves? No. So basically it doesn't possess plane of symmetry, right? So if through any plane, if you cut a substance or cut a compound, then it gets divided into two equal halves and those two equal halves are mirror images of each other. That means the molecule possess plane of symmetry. Okay, for example, if you see on the slide over here, I have taken an equilateral triangle, though it doesn't look like equilateral triangle. I think it's because of my bad drawing, but assume it is an equilateral triangle and then I try to cut it through the center, like horizontal line which I have drawn. Is it, and let's say this is A, this is B and C. Is it dividing into two equal halves which are mirror images of each other? Yes, it does. Let's try for the square. Again, my drawing is very poor, so hence it doesn't look like square, but let's try out cutting it through a certain plane. So if I cut it horizontally, is it getting divided into two equal halves? Yes. Can I cut it through some other plane which is dividing into two equal halves? I can cut it like this and it will divide into two equal halves. I can also cut it diagonally like this and it will get divided into two equal halves which are mirror images of each other. I can also cut it through the other diagonal and then it will get divided into two equal halves. So there are many planes through which it can be cut and can be divided into two equal halves. Look at this circle or sphere. If you try to cut it through, if you try to cut it through a certain plane, and the two equal halves will be mirror images of each other. Yes. If you put the vertical line or vertical plane, if you cut it through the vertical plane, the way how I have done, it will get divided into two equal half circles. I can do it horizontally also, right? I can do it diagonally also, right? So that means these are the substances which possess plane of symmetry. Now let's see few more examples and you tell me whether those things possess plane of symmetry or not. I have written certain words over here Okay, when I say plane of symmetry, as I mentioned, we are looking for the two equal halves which are exactly mirror images of each other. This is something which you have to keep in mind. It's just not dividing into two equal halves. It is that that those equal halves should be mirror images of each other, exact mirror images. So what can you do when you're talking about the plane of symmetry? When we are trying to find out the plane of symmetry, what you can do is, let's say I have taken a circle, or not, yeah, so let's say if I have taken a circle, I was giving you the example of circle just 1 minute back. So let's say I have taken a circle, and if I want to see whether it possesses the plane of symmetry or not, what I'll do is, at a certain plane I'll put a mirror. I'll not look at the other half. I will not see what is the other half, and I'll try to draw the mirror image of it. And if the mirror image is exactly the same what is already there in the second half, that means it possesses the plane of symmetry. So for example, let's say I have put a mirror over here. Okay, now I'm saying that this is the mirror. Okay, so if this is my first half, this is my first half, I will try to draw the mirror image of it. So this is how the mirror image will come, exactly this way. And if the mirror image is coming, what we are drawing, if it is the same as what is already given in the second half, that means it possesses the plane of symmetry. Though you can, or most of the time you can see and you can analyze and you'll get it, but there would be some cases which will become a little confusing, whether these halves are mirror images of each other or not. In that case, you draw the mirror image and see whether it's same as what is the other half or not. Okay, so let's try with these questions. Let's see whether these molecules possess plane of symmetry or not. Can this be divided into two equal halves? Yes, I think I can divide it by putting the vertical mirror, or I can do the vertical slit or vertical cut, and we will get the mirror image of it, right? Now, similar way, I can cut it from here and we'll get two equal halves and mirror images of each other. Same thing I can do with C also. Same thing I can do with D also. Vertical cut. What about E? Yes, we can do it. You can cut it through this plane and it will get divided into two equal halves. So now look at this F and tell whether it can be cut into two equal halves. Assume that F is not planar. Okay, assume that this is not in the same plane, or it's not planar molecule. Then can we cut it through any plane? No, we cannot. This doesn't possess the plane of symmetry. So now let's look at N. Okay, so now this is the N letter. Okay, and now we are trying to find out the plane of symmetry over here. So it seems like vertically there is no plane of symmetry. Horizontally also there is no plane of symmetry. You can try it out on your own. And then let's try out if diagonally we have it or not. So this is my diagonal. I have put a mirror. I told you how to check the plane of symmetry. When you are checking the plane of symmetry, it's good if you can see whether the other thing is mirror image or not. But if it is confusing, because you'll try to generally match with the other part of the molecule or other part of the substance, it is preferable that you hide the other part from where you have cut and then try to make the mirror and try to make the mirror image on your own. Okay, so let's do one thing. Let's completely ignore this. Okay, now we don't know what is here. Okay, I'll rub it off in 2 minutes, by the way. So now try to make the mirror image and see whether it is matching with the other half or not. So here, this is the point. Let me just put some points. This is the point. Let me try to make the mirror image of this. The point comes here. This is the point. Here comes its mirror image. Here is the point. Here comes its mirror image. So with the 3 points itself, we can see that here is nothing what we are getting in the another half. So this line is definitely, or this other half is not the mirror image of this part. I had put the diagonal over here. I had put diagonal here. I had put the mirror here. Okay. This is my mirror. This is, so diagonally I have kept my mirror. And here is what I'm getting the points. So this would be the mirror image, whereas in the actual molecule, where is the other line? So basically, this is your N. This is nowhere the mirror image of this. Okay, so hence it does not possess the plane of symmetry. I hope you understand what exactly I'm telling you. So you talk about N or you talk about Z. Isn't this the same thing? When you talk about Z, again you'll put a mirror over here and you'll try to form the mirror image of it. So you have put a mirror over here, and when you try to form the mirror image will not come here. This is not the mirror image. Instead, the mirror image will come here. This will be the mirror image, right? So though it looks like N and Z have the plane of symmetry, but they doesn't have. and hence these do not possess the plane of symmetry. So what do you have to do when you are getting confused? Put the mirror, try to make the mirror image and see whether it's matching with the other part or not. Now this K has the plane of symmetry. Yes, it does, like this. Okay. Does this M has the plane of symmetry? It has, through this vertical plane. My verticals are a little shaky and basically are not very straight, but I hope you're able to understand. So if I'm putting this plane from the center, then it is possessing the plane of symmetry. So this is how we understand the plane of symmetry. Now let's take some examples of actual molecules which we are going to deal with, and we understand the plane of symmetry over there. So first thing which I'm going to take is an unsaturated molecule, and there I'll show you how to check the plane of symmetry. You can see the compounds I have written over here. So I have written cis and trans form of C double bond C CH3 H H H. So these two CH3s are on the cis form in one example, and in the other they are in the trans form. We have to see whether these possess POS or not and COS or not, though COS I have not explained to you yet. So once we will understand COS, we will come back to these molecules and we'll see whether these possess the center of symmetry or not. So let's first figure out whether the plane of symmetry is there or not. So now all of us know that these molecules which are unsaturated are planar molecules. These are planar molecules, right? So all these attachments, the carbon, CH3, hydrogen, all these are in the same plane. How exactly they look like? So this is my cis form. If you can see, this is planar molecule. These two dark blue color balls are representing the carbon. This pink color thing is showing the double bond. Here is the hydrogen and here is the CH3s. Okay. Now tell me whether this possesses plane of symmetry or not. Yes, it does. If I cut it through this, won't this form the mirror image? I mean, the two equal halves are mirror images of each other. This is one plane through which we can cut. Other plane is I can do the slice cut, right? These are balls. I mean, these are spherical items, and when you cut it, they'll cut into semi halves, right? So you can even do the you can even do the slice cut and you will be able to get the two equal mirror images of each other. So two halves you will be able to get. So two plane of symmetries it possesses through this way and the slice cut. So basically horizontally, not in horizontal also you are basically cutting it like a slice, right? So this possess the plane of symmetry. So does this possess plane of symmetry? Yes, it does. Right? Now let's talk about the trans. So what is trans molecule? This is my trans molecule. Again, this is planar. It's not going to be non-planar if it becomes trans. So this is my planar molecule. Now does this possess the plane of symmetry? If I cut it vertically, no, it does not. If I cut it like this, no, it does not, right? But if I do the slice cut, all the spheres will be cut into halves, everything will be cut into half, right? And these two halves will be mirror images of each other. Yes, they will be, right? So you will cut the slice cut and then you'll get the two equal halves which are mirror images of each other. So even trans possess the plane of symmetry, but the plane of symmetry is not vertical, plane of symmetry is not diagonal. The plane of symmetry is in the same plane in which the molecule lies. The molecule lies in this plane, and in the same plane if you do a cut from the center, it possesses the plane of symmetry. So plane of symmetry in trans is there? Yes. Here we have to note a very important thing. Please make a note. Any planar molecule will always possess at least one POS. We are not going to check how many POS are present. We are going to check whether POS is there or not. Okay. So any planar molecule will always possess at least one POS. And what kind of POS it will be? When you do the slice cut in the same plane in which the molecule lies. Okay. So it will always have a slice cut POS. Which all POS it had? It had this one had the vertical one and the slice one, and this one is slice. So it's not only for these two cases, but any planar molecule you can do the slice cut and you will get the two equal halves which are mirror images of each other. That means that cut should be in the same plane where the molecule lies. So these are the two examples where we have understood the POS is present or not. Let's see a few more examples and try to figure out whether POS exists in those molecules or not. Okay, so now you have got a better idea how a planar molecule will look like. Now you look at this molecule and tell me whether there is a POS or not. Think about it. It has 4 different groups attached in both the carbons. So if you try to cut it through this way, no, you cannot cut it. If you want to cut it diagonally, you cannot cut it into two equal halves. But if you want to do the slice cut, because it is a planar molecule, you can cut it. Hence, this possesses POS. It has POS. Okay, so let's talk about the next example. Next example is dichlorocyclopropane, and now we have to see whether this possesses POS or not. For this also I have kept a model, but mind it, this is for the initial stage. I'm keeping the models. You, for all other compounds, what we are going to deal with in future, you have to think on your own, and if you have to see whether the molecule can be divided into two equal halves as the mirror images or not. So initially, to get a better understanding, I'm showing you some models. This is my cyclopropane with two chlorines attached. So these blue things are chlorines, and now let's see whether this possesses POS or not. So can we cut it in certain way that it gets the plane of symmetry and it gets divided into two equal halves? If I cut it like this from the center, like vertical cut, my this sphere will get divided into two equal halves. This will get divided into two equal halves. This whole part will go here, and this whole part. So this is mirror image of this. This is mirror image of this. And even the lower sphere, what is here? Look at it carefully. Okay. I can cut it like this. I can cut it like this. And everything will get divided into equal halves. These two spheres will get divided into equal halves. This part is the mirror image of this part, right? This is the mirror image of this, this is the mirror image of this, and we can cut it into equal halves. So yes, it does possess the plane of symmetry. Can I do the slice cut? No, slice cut will not give me any plane of symmetry, or the molecule will not get divided into equal halves. Can I do the diagonal cut? Any diagonal cut? Any diagonal cut will help? No, diagonal cut will not help. So only vertical cut will give you the plane of symmetry. So does this molecule possess symmetry? Look at this molecule, all of you guys. I hope you are able to see what exactly I'm showing you. Okay, so basically what I'm doing is I'm cutting it into two equal halves like this, right? And you will get the plane of symmetry. So these two halves will be mirror images of each other. So does this possess plane of symmetry? Yes, it does possess the plane of symmetry. The next compound I have taken is again the cyclopropane. But now what is the difference between this cyclopropane and the previous one? In this, both the chlorines what we had were in the same plane. Basically, they were in the same side. And here, this is one is cis and another is trans. One is towards the viewer and one is away from the viewer. So this is how the representation is. So this is chlorine. This chlorine is the one which is shown by wedged shape thing. So this look at the slide. This is my wedge shaped chlorine. This is my wedge shaped chlorine, and this is my dash shape. So this is how I'm looking at it. So this is towards the viewer and this is away from the viewer. Right now, if I want to figure out whether the POS is there or not, see, slice cut is not giving you any POS, that we had seen earlier also. And if I cut the diagonal also, it is not giving me any kind of POS. The only POS what we were getting in the previous case was through the vertical cut. Now see whether we can get a POS through the vertical cut or not. If I'll do the vertical cut, this part is not the mirror image of this. This part is not the mirror image of this. Though these two white balls will get divided into equal halves, but we are not getting mirror images over here. So even vertical cut is not giving you the mirror image equal halves. If you cut it like this, then also you're not getting the two equal halves, right? If you cut it like this, are you getting the two equal halves? No, we are not. Slice cut is also not giving me the two equal halves. So when I cut it like this is not the mirror image of this, and hence anyway I'm not able to get the mirror images no matter whichever way I cut. So see how this molecule is. This is how this molecule. Okay, neither this cut is giving me mirror images, nor this kind of cut is giving me mirror image, nor diagonal cut is giving me mirror image. So none of the cuts are giving me the mirror images. Look at it very carefully. See and try to relate. Any plane of symmetry? Anybody? Do you think there should be any plane of symmetry over here? I don't think so. Okay, so no plane of symmetry for this molecule. Can POS exist? No, it cannot. Now look at the another molecule. What I have cyclobutane with two chlorines. Both are towards the viewer. So it's like this. So this is how it is. I have not kept the model of it, but that's how it is. This is, so if you see, it's like this. Okay, now see, now tell me whether we can cut it into two equal halves or not. If I cut it like this, so this is basically, that is rhombus and this is rectangle, so definitely makes a small difference. But if I cut it through the center, If I cut it like this, won't it form the mirror image? It will form the mirror image, right? So this part is the mirror image of this part. You can cut it vertically and you will get the equal half, which is the mirror image of the other part. So POS is present. Yes, it is present. So now see, this particular compound, I have shown it like this. So this is how it is. This is cyclobutane, and one chlorine is up here and another chlorine is down here. If you do the cut, the vertical cut, it will not give you the equal halves. You do the slice cut, it will not give you equal half. But if you do the diagonal cut, your sphere, your this sphere will get divided into two equal halves. Then your cycle will get divided into equal halves, and the other sphere will get divided into equal halves. So hence you will get what? I mean, see, these bonds are there. There are no lines like this. This is all spherical over here. So this is direct attached. It's like this. It's a direct attachment. Okay, and this is also direct attachment. So don't get confused by the lines over here. So it's not actually line. This is, these are actually spheres over here, right? So when you will cut it, these spheres are directly attached, and the half sphere will go that side and half cycle will go that side. Similar way, half sphere will come to this side. Similarly, for down, half sphere will go that side, half sphere will come this side, and the cycle will break into two parts, right? So this is going to give you the mirror image from the center. So does this molecule has POS? Yes, it has POS. Why? Because you are cutting diagonally, your spheres are cutting into half, then your cycle is cutting into half, and then again the down sphere is cutting into half. So even if one is away from the ear, one is towards from the ear. Okay, so let me show you the actual thing, because I don't think I'm able to tell you this in 2D very well. So let me take the model. Okay, so this is the model, right? Now if I do this kind of vertical cut, is it giving me POS? If I'll do this kind of cut, is it giving me POS? No. But if I do the slice, if I do the vertical cut like this is the mirror image of this is the mirror image of this. When I'll cut it half, even my cycle will get even my cyclic ring will also get cut into equal halves. Then these spheres will get cut into equal halves. This bond will get cut into equal halves. And similar way, when you'll cut it like this, everything it's like a slice cut like this. It's you're cutting it diagonally. So half of it will be this side and half of it will be the other side. So you can cut it, but you can cut it like this. You will have to cut like this. So you're slicing it, but slicing it like this from the center, and then slicing this part also. So half of the balls will half of the these atoms will go this side, and half of the cycle will go this side, and half of these atoms will come this side, and half of the cycle will come this side. And these are mirror images of each other. Just see, look at it. Cutting like this, basically breaking the cycle into two, breaking the bonds, breaking the spheres into two halves, one here, one this side, one here, one this side, one here, one this side, one here, one this side. So that's how it can possess POS. So now we have understood what is POS, and we have got the details, and we have understood if a molecule has given how to find POS in that molecule. Now we are going to discuss about center of symmetry, which is the second important symmetry element which should be missing from a compound if compound needs to be chiral. Okay, so what is center of symmetry? Center of symmetry is nothing else but when you pass a line, a straight line through the center of the molecule, then in the opposite directions at the same distance, the same groups must be present. For example, if I talk about this molecule, just look at this molecule. What's happening here? This is an sp2 hybridized molecule. It is a planar molecule. Here is the center of the molecule. If I pass a straight line, this is my straight line. Okay, I mean I don't have a bigger thing, but if you draw a straight line at the equal distances, do we have the same groups present here? No. This purple one represents the one group and the white one represents the another group. This is a cis isomer of your alkene, right? So when you draw the straight line at the equal distances, no same groups are present. That means this molecule does not possess center of symmetry. But if I change it like this, now this has become a trans molecule, and from center of the molecule, if I draw a line, we get two same molecules in the opposite direction. So no matter where So no matter whichever direction I draw the straight line in, I must get two same groups. So if I'll draw a straight line like this, we have two groups, same groups in the opposite direction with respect to each other. This is called center of symmetry. Now I have taken this cyclobutane thing with two groups attached to it, two different functional groups. Assume these two groups are chlorine. Okay, now one chlorine is over here, another chlorine is here. Basically they're in transformation. Now center is somewhere here in the middle, in the space, right? Now if I draw a straight line, passing through the center, if I draw a straight line passing through the center, does it connect the two same groups in the opposite direction at the equal distance? Yes, they do. Just see, this is one here. I'll draw the straight line which will cross the center, come here, and the same group is present over here. Exactly same thing is for this. I draw a line from the center. This group will get, this group is in the opposite direction of this, and it is meeting at the equal distance. When you draw the line from the center, aren't this group and this group, these two groups are in the opposite direction at equal distance? Exactly same thing is for this group and this group. Exactly same thing is for this group and this group. So basically all the groups which are present are, when connected through a line, through a straight line from the center, they are at the equal distances and they are the exactly same groups. So this is called center of symmetry. But if I would have made a change in this molecule like this, if I would have made it cis rather than trans, the other one was the trans molecule. Now this is a cis molecule. Now when you pass a line through the center, all the groups are same at opposite directions. But when you talk about this one, you draw a line through the center, this group and this group, these two groups are not same. Basically when you are talking about cis are in the same plane, so they are not basically connected through the straight line which is passing through the center, so they are just facing each other. This group is actually diagonally opposite when the line is passing through the center and is at the equal distance. Okay, so that means there is no same group in at least one pair of the group is not the same group, or two pair of the groups are not the same groups in the opposite directions. Hence this molecule does not possess center of symmetry. So now we have got it, what exactly is the center of symmetry. You have to pass a line from the center and see whether the groups where it is getting connected is the same set of groups or not, and are at the equal distance or not. So this is called your center of symmetry. So let me just show you how it actually looks like if you have to now let me show you how actually it looks like when you see on the plane of the paper. This one is your molecule, and here you have this is the carbon, this is the exact this arrangement, but yeah, we have I think 4 different groups and I have taken only 2 different groups. The COOH is on the trans position and the straight line is passing through that center, and hence these COH and COH are at the equal distances. Exactly same way CH3, when is at the trans positions, when the line is passing through the center, they are at equal distances in the opposite direction. Same way if you talk about hydrogens are, look at this hydrogen and this hydrogen, these are also at the equal distances when the line passes through the center. So this is basically what is center of symmetry means. Okay, so whenever you get a question, you have to check both of the things. One is plane of symmetry, one is center of symmetry. You have to imagine a particular molecule and then you have to see its 3D representation in your imagination, and then you have to see whether a line when passes through the center is actually giving you the same groups or not. And second thing, when you cut it through any plane, is it giving you mirror image or not. If both are present, POS and COS, then the compound will be optically inactive. Even if one of the two are present, then also the compound will be inactive. The only condition where the compound will be optically active will be when both of these symmetry elements are absent. So basically POS must be absent and COS must be absent. Both of them together must be absent in a molecule to make that molecule optically active. Until now, I have shown you POS and COS, but we didn't speak about anything with respect to chiral centers. So that means chiral centers are not affecting the chirality of the molecule and the optical activity of the molecule. So presence and absence of chiral centers will not make any difference, or will not affect the chirality and optical activity of the molecule. So let's see a few more examples. Let's understand in depth. Now we have understood the concept. What we have to do is implement the same concept and see how different compounds behave, or how different compounds can show optical activity or chirality, or where in which all cases they cannot show optical activity or chirality. So let's begin with the examples now. So here I have listed some structures, and we will be finding out multiple different things. We will be checking out if we have a chiral center in the compound. So CC is nothing else but chiral center. Okay. If we have plane of symmetry, if we have COS, and then if the molecule possesses chirality and shows optical activity or not. Okay, so let's begin with the first structure. First structure is carbon, one single carbon with 4 hydrogens. That means all the 4 groups are same. So this definitely does not have a chiral center. What is the meaning of chiral center? That we must have 4 different groups attached to it. So first thing which can be very clear is that there is no chiral center present over here. Okay, then comes the POS. So let's see whether the POS is there or not. This is my molecule. See, all the 4 groups are same. Okay, now to check POS, we will have to cut it through certain plane. If I keep my molecule like this and cut it vertically, what will happen? Half of this atom will go this side, half of this atom will go this side. Similarly, half of this atom will go this side and half this side. One group here and one group here. So both of the whole thing will get divided into equal two halves, which will be exact mirror images of each other. So does this molecule possess POS? Yes, it does possess the POS. But do we have any COS here from the center? If I pass any line, this carbon itself is the center. So if I pass any line, are you getting the equal and opposite at a group at the equal and opposite position when you pass a straight line through the center? If you pass a straight line through the center, where does its center even lies? It is, let's say here, this. So we don't have an equal and opposite. At equal and opposite distance, there is another atom present here. So no COS in this molecule. Does this molecule possess chirality? No, it does not, because the condition for chirality is in the molecule the POS and COS must be absent to be chiral or to show the optical activity. So even though there is no COS present, but POS is still present, and hence it will not have the chirality, and hence it will not show the optical activity. Exactly same way, let's try out the other compound. Other is what? In other case, we have removed one hydrogen and we have placed one chlorine over there. So it's something like this. This is how the structure is. Okay, now let's see whether this possesses the POS or not. So if I take the molecule and if I cut it, so if I cut this molecule through this plane, okay, like this, if I cut it like this, what will happen? Half of the chlorine will come this side, half of the chlorine will go this side, half of this hydrogen will come this side, half of the hydrogen will go this side. This one hydrogen will go this side and this one hydrogen will remain at the another end. Just look at it. So we are cutting it through this plane, right? And then will we get the two equal halves? Will we get the two equal halves which are mirror images of each other? Yes, exactly. We are going to get the two equal halves with the mirror images. So basically, when we are cutting it through this, these two atoms are dividing into half, whereas this one hydrogen is coming this side, one hydrogen is coming this side, which are exactly at the mirror image of each other. And hence, we are getting the two equal halves which are mirror images of each other, and it still possesses the POS. Okay, COS will not be present in this molecule as well. So POS is there, no COS, no chirality, no optical activity. Now let's see if I change it to some other group. Let's say I remove one more hydrogen and I add some other group. Will now it stop showing the POS? This is the group. Okay, now two hydrogens and two other different groups, chlorine and bromine. Again, I'll take the same plane, cut it like this. What will happen? chlorine will come, half chlorine will come this side, half chlorine will go that side, half bromine will come this side, half bromine will go that side, and one hydrogen this side and one hydrogen that side, and carbon will be divided into two equal halves. So isn't it making the equal halves in the mirror images of each other? Yes, it is. So it still possesses POS. Okay. So even when we have removed two hydrogens and kept two different groups over there, it is still possessing POS, and hence no chirality, no optical activity. Now, what if I change it to one more group? If I change one more group, will now it possess POS? Let's see. Now, let me take again the same plane and cut it through this. Definitely, my chlorine, half of the chlorine will come this side, half that side, bromine, half this side, half that side. But what will happen when the carbon will cut half into half from the center? This side is one hydrogen and this side is your fluorine. So basically two different groups we have, and when we'll cut it into half, neither they are the same, neither they are the exact same images of each other, not the equal halves, because this is fluorine and this is hydrogen. So that's why now it will stop showing the POS. And if you remember, I told you that any sp3 carbon with all the four different groups present in it, when we have only one chiral center or one chiral carbon present, in that case it actually do not possess any kind of symmetry element. That means all the 23 symmetry elements are absent, and hence it makes the ideal condition for a compound to be optically active. So this is the ideal molecule to be optically active because it does not possess any kind of symmetry, and hence no POS, no COS. Chirality, yes. Optical activity, yes. Okay, so I have shown you also how exactly it does not possess POS. COS, because there is nothing which is, in all the cases, the COS story will remain same, that we don't have anything in exact opposite side of the of your molecule or of your atom if the line passes through the center. So that is not only in one case, that is in all the cases. So its structure is like that, at the center when you pass a line you won't get anything in the opposite direction. So it does not possess COS. Now let's look at next set of examples. So now these are the next set of examples, and let's see whether we have chiral center, POS, COS, chirality or optical activity present in these molecules or not. So look at this molecule, what I have over here. So we have a cyclopropane with two chlorines present, and I have shown them with the wedged bond. That means both are in the same plane facing towards the viewer. Okay, so both the chlorines are in the same plane facing towards the viewer. This is the cis isomer of the dichlorocyclopropane. So does this molecule has a chiral center? Let's see. There is one carbon over here which has chlorine. So if I'll resolve it, the molecule will become CH2, CH, CH and Cl here and Cl here. I have already explained you in geometrical isomerism how to resolve the cyclic chain. So this CH2 definitely is not a chiral center, but is this second carbon is the chiral carbon? Yes, it is, because this side it has a different group and this side it has a different group, and then one hydrogen, one chlorine. So basically this carbon is a chiral center, and as well as this carbon is also a chiral center. So we have two chiral centers present over here. But as I mentioned, chiral center's presence does not tell you anything about the chirality of the molecule. So we have to look for the plane of symmetry and COS if these are absent or present. So if I cut my cyclopropane from this carbon, basically these are spherical atoms over here. So what will happen? This top atom will get divided into two halves, and then at one side you will get one carbon and then chlorine. Another side is another carbon and another chlorines. Will they get divided into two equal halves? Yes, they will get divided into two equal halves. Both of the chlorines are facing each other. They are making their own mirror images. The two equal halves are actually mirror images of each other. Hence, it does possess the POS. Okay, what about COS? This is the center. If I have drawn a line from the center, am I getting the same group over here? Is this the same group? Do we have any carbon over here? No. If I draw a line from the center Am I getting a carbon with Cl over here? No. If I draw a line from the center, am I getting a carbon with chlorine in the other opposite side? No. So it does not possess, COS. So does it possess chirality? No. Does it possess optical activity? No. You want to see it a little more live? Let's see it over here. This is my compound. This is what exactly we are talking about. I have cyclopropane over here with two chlorines facing towards the viewer in the same plane. Now, if I cut it through this plane, this atom will get divided into half this side, half this side. We will get one chlorine this side, one chlorine this side. We will get one hydrogen this side, one hydrogen this side, and all of them are making mirror image. I mean, if you cut it from here, this is the mirror image of this, this is the mirror image of this. These two atoms are going to get divided into two equal halves, and each of the this carbon is also going to get divided into two equal halves. So you're cutting like this, you're getting mirror images of each other, and hence this is the POS. Now let's understand whether we have COS in this molecule or not. This is the center of the molecule. You pass a straight line from here. Is there anything present over here which is same as this yellow ball? No. When I pass a line through the center, am I getting anything here? This should be the location. I think this will be the location where I expect a same group to be present. So it's not present over here, nothing is present over here. This is an empty space. Basically on the equal and opposite direction, there is no same group is present, hence it does not possess COS. So I have shown you for one, and rest of all you will have to think on your own. Every single time when we are solving the question, we won't have these 3D structures to get the clear picture. So you will have to imagine it in your mind, and then you will have to solve the question. Try to make as many imaginary pictures. I mean, try to basically make a 3D representation of the molecule in your mind. Right now I can show you the 3D structure, but you won't get it all the time, and hence your imagination works better, or you can say your mental eye, where you have to think about the 3D structures, is more important than having these structures in front of you. Okay, so let's talk about the next example. Chiral centers will still be there because the molecule is same. Chiral center is there, yes. Does it possess POS? We need to see. How will we see whether the POS is present or not? Again, we will cut it through a certain plane and we'll see whether it is getting divided into two equal halves or not, and those two equal halves are mirror images of each other or not. So basically, if I cut it through this plane, am I getting two equal halves? I mean, my bad, from here. No. Why not? Because one chlorine is towards the viewer and one chlorine is away from the viewer. So it is like this. One chlorine is like this and one chlorine is like this. So these are not mirror images of each other. Okay, so this plane cutting is not giving me, so vertical cutting is not giving me. If I cut it like this, it's not giving me POS. If I cut it diagonally, let's say from any end, let's say I cut it from here. Just a minute. If I cut it like this, or like this, am I getting two equal halves? No, I am not. So even though chiral center is present, plane of symmetry is not present in this molecule. COS earlier was also not present in the molecule. So chirality, yes. Optical activity, yes. Okay, now let's talk about the next example. In next example, we have three chlorines towards the viewer. So this is how the molecule structure is, but I will not show you the POS in the molecule structure. You will have to imagine on your own. So this is your molecule. So I have all the three chlorines facing towards the viewer. This is how the molecule looks like. Now we have to find out whether we have chiral centers present or not, and then does it possess POS or COS. So chiral centers, earlier these two carbons were the chiral centers. Why? Because there was a difference in the structure of the carbon, or you can say there was difference in the configuration of the carbon this and carbon this, or basically the molecule was not symmetric. Now here in this case, if you'll see, the molecule is CHCl, CHCl, CHCl. So if you'll go this side to resolve for this carbon, the same set of groups are there. This from this side and this side you are getting the same set of groups. So this carbon is not going to be chiral. Exactly same way when you'll go for this particular carbon, if you'll go this way and this way, you're getting two same set of groups. Hence both of the carbons are not chiral. As well as for this carbon also, it is the exact same situation. You have CHCl, but this group is also same as this group. Okay, I hope I don't have to repeat how exactly we are getting this, how we have to resolve the cyclic chain. This we have already done in the geometrical isomerism. So that's the reason why I'm not showing you this in very much detail. Okay, so no chiral center. Do we have plane of symmetry? Yes, we do have. Cut it from this plane and you will get the plane of symmetry. So plane of symmetry is there. Do we have center of symmetry? Center of symmetry is not here in this structure itself, because on the opposite direction there is nothing present, it's just space. So no COS. Does it possess chirality? No. Does it possess optical activity? No. Look at this molecule now. In this molecule now, two chlorines are towards the viewer and one chlorine is away from the viewer. So will this make any change in the POS of your, because chiral centers will still be there, COS will not be there. Is it going to make any change? Is it going to make any change in the POS? Let's see. So no chiral centers, no COS. Let's figure out if POS is there or not. If I cut my molecule like this, so what will happen? There are two chlorines which are towards the viewer. One will go to one half, another will go to another half. And on the third carbon, there is the another chlorine present which is away from the viewer. And from that exact plane, I am cutting. So basically, that chlorine will half go to one side and half go to the another side. So basically, your down chlorine, the one which is away from the viewer, is getting divided into equal halves, and the chlorines which were towards the viewer, one is getting into one half, another is getting into the another half. So am I not getting the two equal halves? I'm actually getting two equal halves, and those two equal halves are mirror images of each other. Let me just show you this again. This is how the molecule structure is. Two towards the viewer, one is away from the viewer. So if I cut it through this plane, basically I cut it like this. Okay, I cut it like this. I cut it like this. What will happen? This hydrogen will get divided into two equal halves. This chlorine will get divided into two equal halves. At one half you will get one chlorine, another half you'll get another chlorine, and your molecule will divide into two equal halves, right? So this possesses POS, hence no chirality, no optical activity. Okay, now let's move to the next set of molecules very quickly, and now I'll try avoiding showing you the 3D structure. Think it on your own, or what we can do is I can stop for a while, or you can pause the video, try filling this table on your own, and then let's verify with mine. Now these are some examples. Try out them on your own, pause the video, imagine the 3D structure, try them and see whether you are able to solve them or not, or what answers do you get, and then we will discuss. So now, starting with the ninth question, what we have: one chlorine, two bromines, basically two same groups in one different group, all three facing towards the viewer, right? Now, one is the chlorine over here, one bromine here, and one bromine here. Does it possess chirality? Let's see. First, we will check whether the chiral center is present or not. So this carbon seems chiral and this carbon also seems chiral, right? So we have chiral centers. Does it has POS? If I cut it through this plane, so basically one chlorine which is on the top, from there if I cut it, it will get divided into two equal halves. This chlorine half will go this side, half will go this side, and this bromine, one whole thing is on one half and another bromine is on the another half, and they are forming mirror images of each other, right? And hence it does possess POS. Does it possess COS? This whole structure itself does not possess any kind of COS, so no COS. Chirality? No. Optical activity? No. Go to the next compound. Exact same situation is there. Only difference is the chlorine, all the three groups which were towards the viewer earlier now are away from the viewer. So now you have two bromines towards the viewer, one chlorine away from the viewer, right? Cut it again in the same way. What will happen? Your chlorine will get divided into two equal halves, one half this side, another half this side. One bromine and another bromine will be in the one part. So aren't they forming the mirror images of each other? How exactly it is, let me just show you, if just in case you want an assistance. This is how it is. Okay, two bromines on the top, one chlorine down here. I will cut it like this. So this hydrogen half will go this side, half will go this side. This bromine will go half this side, half this side. One side will have one complete bromine. Half chlorine will go this side, half chlorine will go this side. One bromine completely this side, one bromine completely in the another side, and dividing it into this vertical half will make or will break this molecule into two equal halves which are mirror images of each other. Hence this possess POS. Chiral centers, yes. POS, yes. COS, no. Chirality, no. Optical activity, no. Now let's understand in the next compound what is the difference. Now what we have is one bromine and one chlorine facing towards each other, and one bromine is away from the viewer. So what exactly is the configuration now? Let me just show you, because that will give you a better picture, but till then you can imagine and think how it would be happening, and whether we can whether this molecule can possess POS and COS or not. So this is how the arrangement is. This is my chlorine, this is my bromine, this is my bromine. If I use the same concept altogether, what I have used till now, that cut it vertically, what will happen? Hydrogen will go this side, hydrogen will go this side, this bromine will go half this side, half this side. And in the two halves, one side we will have bromine, another side we will have chlorine. Is it getting divided into two equal halves? No, it is not getting divided into two equal halves, right? So this kind of configuration will not have POS. Chiral centers, yes, we have POS. We don't have COS, was anyways was not there. Now does it possess chirality? Yes, it does. Does it has optical activity? Yes, it does. Okay. Now next compound, we have two different groups. One is chlorine, one is bromine. Just think on your own. It is a simpler version of what we have done just now. I'll cut it from here. I'll not get two equal halves. If you talk about the chiral center is present. This is the chiral center and this is the chiral center. This is the chiral center in the previous case. This is the chiral center in the previous case. So chiral centers are present. How many chiral centers are present? That is not important. Even if one is present, we are bothered. We are just checking whether chiral centers are there or not. And the presence and absence is making any difference in the chirality or not. So, do we have POS here? No. Do we have COS here? No. Do we have chirality? Yes. Do we have optical activity? Yes. Okay, so we are done with these examples. Let's go to the next set of examples. Again, you try them on your own and then we will verify the answers with mine. So now these are the next set of compounds. Note them down, pause the video, try the same thing what I have done till now. Try to find out the chiral center, POS, COS, optical activity and chirality, and then I will discuss with you. But pause the video and do it on your own. Do not wait for my explanation for these compounds. Okay, so let's go to the first structure. What we have, the structure is something like that. This is chlorine and this is chlorine. So basically two chlorine atoms on the cyclobutane facing towards the viewer like this. I mean, they are towards the viewer, so they both chlorines are on the same plane. Does this molecule has chiral centers? Let's see. This particular carbon has hydrogen and chlorine. Let's see if both ends are same or different. So here this part is symmetric to this part, and hence it is not a chiral center. This carbon cannot be a chiral center because it has two hydrogens. This carbon can also not be a chiral center because it has two hydrogens, and this carbon also, the same story is there. This half and this half is symmetric and hence no chiral center. So no chiral center is present over here. Let's see if we have POS or not. For POS, as I mentioned that two of the chlorines are facing towards each other, I can cut it into two equal halves like this. So basically anything which can if I choose a plane which cut these two balls into two equal halves like this. So basically I'm cutting it through the center like this. So your chlorine balls will get divided into two equal halves, one this side, one that side. This chlorine also will get divided, one this side, one that side, and then the molecule will be divide and this is half of the molecule will be that side and half of the molecule will be this side. This is one plane through which it can be cut, or you can cut it like this and still you'll get the two equal halves. So there are many ways you can cut it and the plane of symmetry will be there. We just have to see whether plane of symmetry is there or not by cutting through any plane. Okay, so this is the molecule what I'm talking about. If I cut it like this, what will happen? The things will get divided into two equal halves, and there this is the mirror image of this. This is the mirror image of this, and hence you'll get two equal parts with the mirror images of each other. Or simply I can cut it like this, and then also you'll get two equal halves with the mirror images of each other. So it does possess POS. POS, yes. Let's see if the COS is there or not. So I have to pass a line through the center. This is the molecule. I have to pass a line through the center. This is the center. If I'll pass a line through the center, am I getting the equal and opposite at an equal and opposite distance, the same group? Look at this hydrogen at equal and opposite direction. There is one hydrogen. Okay. Look at this chlorine, and at equal and opposite distance, am I getting chlorine over here? No, it is hydrogen. So when the line is passing through in the equal and opposite distance, you're not getting chlorine, you're getting hydrogen over here. So basically, even if one differs, that means COS is not present. So no COS over here. Chirality, no. Optical activity, no. Okay. Now let's move to the next part. Chiral centers, no. POS, because the molecule is same, hence I have directly written it over here, because only difference was in cis and trans. Now let's talk about the POS. Does it possess POS? Let's see. Let's see whether it possesses POS or not. Again, what can we do is we can cut it through the plane. We can cut it through this plane. This plane. Okay. So what will happen when I'll cut it through this plane? This plane or this plane. Yeah, I mean basically like this. So basically this cycle will get divided into equal halves. This atom will be half, this atom will be half, this atom will be half, this atom will be half. Half of the part will go to this side, half of the part will go to that side, half of the part will go to this side, half of the part will go to that side. So aren't they forming exact halves of each other, which are mirror images also, because this is the mirror image of this is the mirror image of this, and these have been divided into two equal halves. So these are exact mirror. So these semicircles which will form after breaking are mirror images of each other. So it does possess POS, no matter the chlorine was in the cis position or was in the trans position, it is still possessing POS. So POS is present, yes. So I think we have COS. We have COS. If I draw a straight line through the center, I am getting the same group in equal and opposite directions. And same is the thing for the other groups also. So this molecule does possess COS. Earlier one was not, but this one possess, because you will pass a straight line and you will get the chlorines. In all of the cases, it is hydrogen. So they are same groups in the equal and opposite directions when you pass a line through the center. Earlier, the molecule was not possessing center of symmetry. Why? Because both the chlorines were facing each other. They were not in the opposite direction with respect to each other. Here, now they are in the opposite direction with respect to each other. And hydrogens are anyways aligned in this way that they are in the equal and opposite distance with respect to each other. Hence, now this molecule possesses center of symmetry. So, center of symmetry is there? Yes. So, both the conditions which we didn't want are present in this molecule. Hence, no chirality, no optical activity. Okay. Now let's talk about the next molecule. Does this molecule has the chiral center? No, it is symmetric from this way also and this way also. Same is the case for this carbon, hence no chiral center. Does it has POS? I can cut it through this plane which can divide chlorine and bromine into two equal halves, and it will possess the symmetry. Okay, so plane of symmetry is there. I'm cutting it through the plane which can break chlorines into two equal halves and bromine into two equal halves. So one part will be here, one part will be there. Rest of the part is anyway symmetric. So POS is present. Do we have COS? No, we do not have COS. Because why we don't have COS? First of all, both of them are in the cis position, your chlorine and bromine, and secondly these are two different atoms also. Rest of the other hydrogens may possess the symmetry, I mean they will be in the equal and opposite direction, but chlorine doesn't have the chlorine in the opposite direction, bromine doesn't have the bromine in the opposite direction. So no COS, no chirality, no optical activity. Look at this molecule now. This is exactly same as this, so I'm not repeating it. You put chlorine or you put bromine, is it going to make any difference? No, it's just two different atoms. So no chirality. POS yes, COS yes, chirality no. Sorry, no chiral center, no POS yes, COS yes, chirality no, optical activity no. Now look at this molecule. What we have, three chlorines facing towards the viewer, and now we have to figure out whether there is. First of all, we have to check whether the chiral centers are there or not. So now this side of the ring and this side of the ring is not symmetric. Hence, we have two chiral centers over here. One is this and one is this. So chiral centers, yes, we do have. Does this molecule possess plane of symmetry? If I cut it from this chlorine, what will happen? One chlorine which is there in the center will divide into two equal halves, and one half will have one chlorine completely, another half will have another chlorine completely. Both are facing towards each other, so they are forming the mirror image of each other, and hence it possesses POS. Does it possess COS? No. This chlorine doesn't have a chlorine in the opposite direction. It does not possess COS. Okay. In equal and opposite direction. So equal and opposite direction for anything which is towards the viewer is away from the viewer, and the same molecule in the opposite direction. That is what will give you the COS. Okay, so no COS, no chirality, no optical activity. Look at this molecule again. Does this possess a chiral centers? Yes, it has chiral centers. It is same molecule as this. Does this possess chirality? Yes. If I'll cut it from this plane, what will happen? The one chlorine which is away from the viewer will cut into two equal halves, whereas these two chlorines which are towards the viewer will go to one half and the another half. So you will have half the structure like this. Okay, half chlorine atom. Okay, I have just drawn the half semicircle so that you can understand. Then we have a chlorine over here, and the another half is also will be like this. And then another chlorine on this side. So these are mirror images of each other, right? So this possess POS. Yes. COS? No, again not, because this chlorine doesn't have the opposite chlorine a chlorine in the equal and opposite direction. Plus both of these chlorines are facing towards each other. So these also don't have the equal and opposite at equal and opposite distance. When the line passes through the center, they don't have the respective chlorines. They both are facing each other and they don't have the chlorine which needs to be in the equal and opposite direction. So no COS, no chirality, no optical activity. Okay. I hope you would have understood, and now you would be much more comfortable in finding out POS and COS for the molecules. Let's try out for the next set of examples very quickly. Now these are the four structures over here. Try them on your own and figure out whether the chirality and optical activity is there or not, and then I will discuss. Just try it out on your own very quickly. Okay, so let's start discussing. We have on all the four carbons, we have chlorines present. All the four chlorines are facing towards the viewer, and the chain is pretty symmetric from this end, and all the carbons, if you look at their left and right, chains are symmetric, hence no chiral centers at all. No chiral centers. Now we have to see whether it possesses POS or not. Yes, it does. It's very clear. You cut it from here, then also it possesses POS. You cut it from here, then also it possesses POS. So POS, yes. COS, no, COS is not there. Okay, though even look like that this chlorine has a chlorine in opposite direction, this chlorine has a chlorine on the opposite direction, but these are not opposite, these are facing each other. When we say that they should be in equal and opposite direction, if one is facing towards the viewer, another one should be away from the viewer. Then only you will draw a line from the center and you will get the same group in the equal and opposite direction. So does this molecule possess COS? No, it does not. All the molecules are like this. Let me just show you. All the molecules are like this, right? And now when you'll pass a line through the center, no chlorine on the opposite side. You pass a line through the center, no chlorine in the opposite direction. Okay, so no COS. Chirality, no. Optical activity, no. Even if one symmetry element is present, there will be no chirality, no optical activity. Let's talk about another example. Now here I have changed the groups. You have fluorine and fluorine over here, and two chlorines. Now all these four groups again are facing towards the viewer. Now still this chain is symmetric from this end and this end, or for each carbon their opposite ends are symmetric, and hence no chiral centers at all. So no chiral centers at all. Just in case if you have any confusion in the chiral centers, please resolve the chain and get it, because that is something which we are not discussing right now. How to get a chiral center, what all four groups are present on the carbons, that has been discussed very in very depth in the previous videos when you were doing geometrical isomerism. So that's why I'm not putting much focus on these chiral centers, and I'm just directly telling whether the chiral center is present or not present. Okay, POS, does it possess POS? Yes. Cut it from this plane and it will possess POS, or cut it through this plane and it will possess POS. So POS is there. Do we have COS? No, because the things are not on the transposition with respect to each other. All the groups are again like this. The only difference is now you have a fluorine group over here and the fluorine group over here. But does it make any difference to the molecule? So does it introduce the center of symmetry in this molecule? No, because again your chlorine doesn't have a chlorine in the opposite direction, your chlorine doesn't have a chlorine in the opposite direction, your fluorine doesn't have a fluorine in the opposite direction, and this fluorine also doesn't have a fluorine in the opposite direction. So no COS. Chirality, no. Optical activity, no. So now look at the next molecule. Do we have chiral centers? No. So now let's talk about whether it possesses POS or not. For showing the POS, I'm using the 3D structure again so that you can visualize much better. This is the molecule what we are dealing with. So basically, this is chlorine, this is fluorine facing towards the viewer. This is chlorine, this is fluorine away from the viewer. That's how the structure is, if you can see it carefully. Okay, now we have to check whether it possesses POS or not. If I cut it through this plane, yes, these atoms will get divided into two equal halves, but will I get the two equal halves when I divide the ring? No. This side we have chlorine and this side we have hydrogen. This side we have chlorine and this side we have hydrogen, so no two equal halves. If I cut it through this plane, am I getting the two equal halves? Still I am not getting two equal halves. If I cut it horizontally, am I getting two equal halves? No, I am not getting two equal halves. Please visualize, please try to understand what I am trying to tell you. When I was cutting vertically, it was actually slitting the molecule into two equal halves and the whole ring into again two equal halves. And the same kind of atom should have been in the opposite direction. Then it would have been a mirror image. But that's not the case over here. This is chlorine. This is hydrogen. This is hydrogen. This is chlorine. If I cut it like this again, no use. If I cut it like slice, is it of any use? No. If I cut the ring like this, is it of any use? No. It's still not giving me two equal halves. So does this molecule possess POS? I don't think so. So no POS over here. Now let's see whether it has COS or not. If I pass a line through the center, do I have an equal and opposite group? Yes. This chlorine is opposite to this chlorine. This fluorine is opposite to this fluorine. This hydrogen is opposite to this hydrogen, and this hydrogen is opposite to this hydrogen. So basically, every single line which is passing through the center is basically giving the say equal and opposite in the equal and opposite direction. You are getting the exact same group. So this definitely possesses COS, and COS in all the directions. So COS is present. Yes. Now here, the reason of not being chiral is not POS, which was there in most of the cases. The reason of not being chiral is your COS. This is a rare example where your chirality is being lost due to the center of symmetry, not the plane of symmetry. So chirality, no. Optical activity, no. Okay, so here your molecule has lost its chirality or optical activity due to the presence of COS. POS is not there in any way, and COS is there in all the ways, in all the directions you have COS in this molecule. Now look at the next compound. Next compound, you have again a cyclobutane with two chlorines facing each other in the cis direction towards the viewer. So does this molecule possess POS? Yes, it does possess POS. Does it have chiral centers? Let me see. So this chain from here and here is not symmetric. So I think it must have center of chiral centers. Does it have COS? No, it does not have COS. I need an equal in equal and opposite direction. I need chlorine. So this molecule is like this. When I'll pass a line through the center, I'm not getting any chlorine over here in the opposite direction away from the viewer. So no COS, no chirality, no optical activity. So I hope you have got it. Let's try a few more questions very quickly. Try them out on your own and then I'll discuss the answers. Okay, so these are the examples. Try them on your own. Give yourself 5 minutes. Solve them in exact same manner how we have solved the rest of the questions and see whether the following compounds possess chirality or optical activity or not, and then I'll tell you the answers for all. So now let's discuss the answers of these questions. Now we have again the group where you have two chlorines present. One is towards the viewer, one is away from the viewer, right? Does this molecule has chiral centers? In the previous one there were chiral centers. Yes, we have chiral centers over here. So let's see whether POS is there or not. If I cut it through this plane, will it give me two equal halves? No, it will not give me two equal halves because one chlorine is up and another chlorine is down. Okay, so and if I cut it through this plane, is it gonna give me anything better? No. If I cut it across the chlorine, is it gonna give me two equal halves? No. If I cut it through this chlorine, is it gonna give me two equal halves? No. So I don't think this molecule possesses POS. So no POS at all. Okay. Do we have COS? Let's see. See, here is the center. I'll pass a line through the center Am I getting the chlorine over here? No. There is one chlorine over here. I pass a line through the center. Am I getting any chlorine on the other side? No. So basically, even though I have one as towards the viewer chlorine, another away from the viewer, but they are immediately at the next positions. They are not on the opposite positions to each other. That's the reason why this molecule does not possess COS also. So no POS. So no POS, no COS. Will it have chirality? Yes, definitely. Will have optical activity? Yes, it will have. Now let's talk about the 24th one. We have cyclopentane with two chlorines attached. Both the chlorines are towards the viewer. Will it possess POS? Cut it through this plane and it will possess POS. Do we have chiral centers? I think we have chiral centers. So these are two chiral centers. Yes, chiral center is there. Does it possess COS? Any plane of symmetry? No, it does not possess any plane of symmetry because opposite to this chlorine there is nothing. I mean, if you pass a line through the center connecting this chlorine, it's like this. And you have one chlorine over here and another chlorine over here. You pass a line through the center. Do you have any opposite chlorine? No, we don't have. So no COS at all. Chirality? No. Optical activity? No. Okay, so now let's see this 25th one. Do we have chiral centers over here? Yes, this one is chiral center and this one is chiral center. So two chiral centers are there. Do we have POS? One chlorine is up, another chlorine is down. Okay, so do we possess POS if I cut it through this plane? No, it will not possess POS. Why? Because one chlorine is towards the viewer and one is away from the viewer. And any other plane you cut it through this chlorine or through the center here or through this chlorine, it is not going to give you two equal halves. Okay, so no POS. Does it have COS? No, because again on chlorine doesn't have an a chlorine at equal and opposite direction, and same is the case for this chlorine. Rest of the we don't have to even check, so no COS here also. So chirality is there? Yes. Optical activity is there? Yes. Look at the 26th one. Now again, do we have chiral centers? Let's see, we have chiral centers or not. So hydrogen is there, chlorine is there, this chain and this chain is not symmetric. So yeah, we have two chiral centers. So chiral centers are there. Do we have POS? I think we have POS. I mean, I have not drawn it properly. This is like this. Chlorine here and chlorine here. This is how it is. So if I'll cut it through this, we will get two equal halves. And yes, it possesses POS. Does it have COS? No. We don't have chlorine in the equal and opposite direction. So no, for this chlorine also we don't have chlorine in equal and opposite direction. So no COS. Chirality, no. Optical activity, no. Let's talk about the 27th one. We have chlorine and bromine in two different positions. Yes, we have chiral center. Do we have POS? No, we don't have POS because if I'll cut it from here, it will not give me any two equal halves. If I cut it through chlorine, it will not give me two equal halves. If I'll cut it through bromine, it will not give me two equal halves. So no POS, no COS. Chirality, yes. Optical activity, yes. Okay, so let's now talk about the last set of questions for today, and you try them on your own and then I will explain you the answers. These are the last three questions of the day, and then I'll give you small notes on the observation of whatever we have done, whatever questions we have done. Quickly try them out and then I'll explain you. Okay, so now let's talk about the explanation of the first one. We have cyclohexane with two chlorines towards the viewer. I mean, does this molecule has chiral centers? Yes, it has two chiral centers. POS is there. If I cut it through this plane, yes, it has POS. Does it have COS? No, it does not have COS because we don't have chlorine at equal and opposite direction. Chirality is there? No. Optical activity is there? No. Now again, two chiral centers are there. Let's see whether we have chiral centers in this case or not. For this carbon, we have a same chain as this side. So this carbon also we have same chain this side as this side. So no chiral centers. Now talk about POS. POS is there. You cut it through this plane, you'll get POS. You cut it through this plane, you'll get plane of symmetry. So plane of symmetry is there. Center of symmetry is there? No. No equal. On the equal and opposite direction there is chlorine, but that chlorine is towards the viewer, not away from the viewer. So we want it away from the viewer. One chlorine should be up, one chlorine should be down. That's how from the center, if you'll pass the line, the two chlorines will be opposite. So there is chlorine present in the opposite direction, but on the same plane. We want it in the opposite, we want it in the perpendicular plane. So no COS, no chirality, no optical activity. Look at this molecule. Again, it will have no chiral centers, and it will have POS. Sorry, my bad. POS along this. Okay. Let me just clean it so that you don't get confused. So I will have POS through this plane. I'll cut it half like this. Half of the chlorine which is towards the viewer will be one side. Towards the viewer, chlorine will be other side. Same way, half of the chlorine which is away from the viewer will be one side, and other part will be another side. So 2 equals half, it will get divided into. Does it have COS? Yes, it does have COS. Let's look at it. I'm passing a line through the center. One chlorine is up, one chlorine is down. They're opposite to each other, and the line is connecting, right? So COS is there. Chirality, yes. Optical activity, yes. Now this is the example where we have no chiral center, and still we have the chirality and optical activity. So this is what exactly we're talking about. The presence or an absence of chiral center does not make any compound optically active or inactive. Okay, so what all observations we have done in today's examples? Let's note them down very quickly first. What is it? First of all, the first observation is, in the even membered ring, if groups are attached on cis and trans position opposite to each other, then POS is definite. That means no matter your two groups are towards the viewer or one towards the viewer, one away from the viewer, in the case of even membered ring, you will do the slice cut like this, and half the thing will go here, half the thing will go there, and it will possess POS in all the cases. So you don't have to always imagine. You can just see if the groups are opposite to each other. No matter they're in cis form or they're in the trans form, in an even membered ring, they will always possess POS. Okay. So this is the observation of today's examples, and this, if you'll remember, it will be easier for you and it will be faster for you. Even if you don't remember, you can imagine, you can see the structure through your mental eyes, and you will be able to see whether the POS and COS is present or not. In next class, we'll do few more questions which are little additional structures, have little complicated structures like allenes and ortho tetra substituted benzene and so on, which we have done in the geometrical isomers also. So all those structures, cumulene, allenes and all that, we will be talking about their optical isomerism in the next class. Till then, you revise that part, you go through that cumulene thing and your spirane thing and your ortho substituted benzene thing, so that you get to understand which groups are out of the plane, which groups are in the same plane, so that the things will be much faster, the process will be much faster, and you will be able to understand the chirality in much better way. Okay, and that will be the last set of examples which we'll be talking about in terms of finding out whether the particular compound is chiral or not. After that, we will be very clear. When we look at the molecule, we will be able to see clearly whether a molecule is chiral or not chiral, or the molecule is optically active or not active. Okay, so let's meet in the next class for next few questions, and then we will start a new topic in the next class, that is the Fisher projection.